All right. Hello, everyone. Is the mic on? Yeah. Okay. Okay. So, anyway, it's my pleasure to introduce to you guys Fidel Alfaro. He's doing his PhD currently at the University of Oxford under Steve Smith. And for those of you who don't know, the biobank is basically his study. Well, he's doing a lot of the analysis and processing on it. He's going to talk to us about it. How you manage 100,000 sets of data. Not only that, it's 100,000 sets of multimodal data with pretty much everything you can imagine. So without further ado, see that. Also, he misses Ramon. He told me to put that.
Who doesn't? Hi, good morning. Thank you for inviting me. As he said, I am Fidel Alfaro, and I'm working in the University of Oxford in the Wellcome Center for Integrative Neuroimaging, which was previously called FMRIB. And I'm going to talk about big data in neuroimaging and about the UK Biobank project. And if you want to interrupt me with questions during the talk, that's okay, because I think this is going to take shorter than was expected. So, okay. For those of you who don't know, the UK Biobank is a prospective epidemiological study that is gathering information of 500,000 people. All of them are residents in the UK, and the age range is 45 to 75 years old. And we are gathering genetic data, biological samples, lifestyle information, and the health records of the participants. And the goal is to discover early markers of disease. This is an outline of the idea of what we want to accomplish, which is gather all these different sources of information, learn from them, and then predict long-term health outcomes to help diagnose of diseases. So first, I'm going to speak, give a brief introduction to the project, the Biobank project. So as I said, it's a epidemiological study with 500,000 participants, and the baseline data was released for all those participants already. And that baseline data includes questionnaires that were filled up by the participants. And those questionnaires include socioeconomic data, behavioral data, the self-reports of psychological state, and also the medical history, including the family. There are also different physical measures, like the typical height and weight, but also the body composition, the grip strength, lung capacity, and, well, many others. We have around 14,000 different variables. And also there are certain biological samples like blood and urine and genetic information. As for the genetic information, all of the participants have their genetic information stored in the database. Originally, there were 800,000 SNPs, which are the basic building blocks of the genetic data. But this was imputed to reach 96 million genetic variants. And all this data was released last July, in 2017. 100,000 of the participants wore a wristband with an accelerometer for a week. And that gives us information about acceleration, but also temperature and light. And that is it gives us better information about the physical activity and about the daylight and sleep patterns in the participants. And it's also, this is more strongly correlated with mortality rates than the self-reports that the participants fill up. And from that information, we get different patterns of physical activity according to the age, and also patterns of sleep that shows us that there's not much difference between evening people and morning people. And well, that's the basic amount of data in Biobank. But recently, in 2014, there was an extension to include different imaging protocols for 100,000 participants. And we are able to scan that many subjects by having 3 dedicated centers to do the scanning. Each of them is scanning 18 subjects per day, so 54 subjects in total, 7 days a week for 5 years. And the imaging protocol includes an MRI of the brain, cardiac MRI and body MRI, and also bone density X-ray and carotid ultrasound. And we hope to get a second extension to do a second scan of 10,000 subjects out of these 100,000 subjects to be able to do some longitudinal studies. This is a summary of the cardiac protocol, the cardiac imaging protocol that was developed in the Queen Mary University of London. It takes 20 minutes and it's using a 1.5 Tesla scanner. And the important part of this protocol is that we get structural and functional information of the heart. But the problem right now is that this data is we don't have an analyzing pipeline yet, so the data is not in the database yet, but it will be soon. There's also a whole body MRI that takes 10 minutes in the same scanner, 1.5 Tesla, and it gives us information of adipose tissue and also the volume of the muscles and the skeleton and of different internal organs, and that information can be used to detect some diseases like inflammation or fibrosis. And this data has been analyzed in an automated pipeline, and it's in the Biobank database right now. There's also an acquisition with a carotid ultrasound acquisition, and both carotids, the right and left, are imaged. And here we have the information of the carotid wall thickness and the carotid plate. And finally, there's a low-dose X-ray bone density imaging protocol. It takes 10 minutes, and it looks at the bone density of the subjects, and it can detect fractures or some problems that you may have in the bones, and also the fat distribution in the body. If researchers can apply for access to the data, this is the link to start that application process. In the application process, you would need to state what is the research that you want to conduct, because you will only be given the data for the kind of research you want to do. There's a fee that every group has to pay, but it's only one payment, and then you have the access for all the data that is generated. And it's £2,000, and the goal for that money is to maintain the computers and the storing capacities. And there's a reduced fee for low-income countries. And every group that uses the data has to follow that process, even us who develop the imaging protocol and analyze the data, we have to also follow this process. And now I'm going to speak about the part of the project that I am involved with this the brain imaging part. This video was released to the media, and it shows what we are doing and what do we want to accomplish. So we are going to measure the volume of different brain structures, also the brain function, the brain activity using functional MRI, brain wiring using diffusion imaging, and we are going to do that for 100,000 subjects. And to give an idea of what this number means, A typical study, well, actually, this would be a big study, is usually 100 or 125 subjects. There are very few studies that are really, really big, like 1,000 subjects. But this is Biobank, and you can see the difference in size is significant. And the question is, why do we want to scan so many subjects? Well, this is an epidemiological study, and the goal is to have the images of the subjects before they develop any symptom. So we don't know what subjects will have what diseases, so we need to scan as many as possible in order to wait for them to develop some diseases. For example, out of these 100,000 subjects, in 5 years, only 50 of them will develop more motor neuron disease, and only 2,000 of them will develop Alzheimer's disease. So that's why we need to scan that many subjects in order to have decent numbers to do comparison and studies. This is a projection of some other diseases that the subjects will develop in 5 and 10 years. So that's basically the reason why we are scanning 100,000 subjects. Sorry. Now I'm going to speak about the imaging protocol and the different modalities that we have. We have 3 different structural modalities: T1 weighted, T2 FLAIR, and susceptibility weighted images. 2 functional modalities: resting state and task fMRI, and 1 diffusion modality with 100 directions. And the whole acquisition process takes 35 minutes per subject. And this has been highly optimized because given the number of subjects that we have, 1 more minute would mean £500,000. So we had to optimize this intensively. And these are more details on the protocol. We managed to have all these acquisitions in 35 minutes by using multiband acceleration for diffusion and functional MRI. As you can see there, the scanner is a 3 Tesla Siemens with 32 channels. We save some time by not acquiring field maps, but estimating them using face encoding reverse field maps with a tool developed in Oxford called TopUp. Yeah, those are basically all the details of the. We were considering adding a 7th modality, ASL, but this was turned down very recently because we want to be as consistent as possible, so we will not be adding any more modalities. This is what we are currently doing with the data, starting from the raw images, the raw DICOMs. Those images go through an automated processing pipeline based on FSL, which is the software library that we developed in Oxford University. Out of that, we get a set of processed nifty images and what we call IDPs, imaging-derived phenotypes, which are basically measurements of different features of the brain, like the cortical thickness or the volume of different structures. And all that information is in the open access database of Biobank. For example, here is how that open access database looks. This would be the volume of the left thalamus, which is one of the IDPs I was talking about, which is basically a number per subject. And in this web interface, you can see, well, the link is up there. And in this interface, you can see several statistics about the population of this variable, the volume of the left thalamus, the mean, and several percentiles. And at the moment, there are more than 4,000 IDPs. And as I said before, more than 14,000 variables that are not brain imaging related. So what are we doing with the images? Let's start with the structural processing. As you know, an important part of any analysis pipeline would be the registration to a common space. And we do that in Biobank by using first linear and then non-linear registration. In that way, we will have all the brains in the same space. And after doing that operation, we can generate our own templates. We have generated templates for each modality, that structural modality that we have, using almost 4,000 subjects. And after that operation, we apply other methods and we get several other IDPs. For example, the volume of the whole brain or different tissues, white matter, gray matter. Also the volume of different cortical regions or subcortical volumes. And another IDPs that we got are the mean or median intensity in a subcortical structure for every modality. And also using tools as FreeSurfer, we get the cortical thickness or the surfaces of different cortical regions. That's what we get from basically the T1. Well, that is from the susceptibility weighted images. Out of the T2 FLAIR, we use a tool developed also in our lab called Bianca, and we get the white matter hyperintensities or white matter lesions. That tool is automatic, and this is a very important. This IDP can be an important biomarker because it's highly correlated with age, and we have not checked that yet, but it can be correlated with some neurological diseases. For diffusion MRI, we run several analyses, like the structural connectivity analysis using basically probabilistic tractography. And also we evaluate microstructural properties of the brain using a different kind of analysis. First, with diffusion, we feed the data to two different models, the DTI model, the diffusion tensor model, but also the 3-fiber model, which is used for probabilistic tractography. And using that model, we have a set of 27 major tracts predefined in the standard space, and we run probabilistic tractography to see those tracts in each of the subjects. And we also, as I said, run a microstructural analysis. We use the DTI information to get to get the fractional anisotropy or the mean diffusivity of every subject. And also using an OD analysis, we get intracellular volume fraction or the fiber dispersion. And what you got in the IDPs are the average across each tract that was previously calculated with the probabilistic tractography of each one of these metrics. So, for example, for the forceps major, you get the average FA or the average mean diffusivity. We also have resting state images, and the analysis that we do on those images is an independent component analysis. So after we separate the components that are signal from the components that are noise, and that is done automatically with a tool called Fix, we get the most common resting state network, like the default network and the sensory motor network. And we use these networks in more complex analysis, like getting the amplitude fluctuations or the functional connectivity, and which allow us to establish a hierarchy of networks using this. The tool in FSL is called NetMats. Sorry, that's a typo there. And we get all that information out of each one of the volunteers, and that would be around 2,500 variables just from the functional connectivity. And finally, the protocol of task fMRI that we implemented was the one in the HCP project, which is the Hariri paradigm, consists basically of showing shapes and faces to the subjects, and the goal would be to find activation in the amygdala and in the visual cortex. And we chose this protocol because it has been extensively used and tested, and it works. The data releases that we have had so far, the last one was in October, and we released the data of 15,000 subjects, and we are working right now in a new set of 7,000 subjects that will be released soon. I said July, but it's not sure. Maybe later than that. Depends on how much time I have. And what you can find in these data releases are the raw images, the processed nifty images that I talked about before, and also more than 4,000 IDPs. And the IDPs are meant to be used by researchers that are not experts in the imaging analysis, or if you don't have the time or the resources to do your own analysis, that is why you can use the IDPs. And there are also the templates I talked about before, for which we use 4,500 subjects. There's one template for each modality. Now I'm going to talk about an important part of what I do, which is the quality control of the images, of the whole set of images. As if you have worked with MRI, you know that it's not uncommon to get this kind of artifacts or problems in the acquisition. Most of them are due to movement in the subject. Those problems can be ghosting or wrap around, or also field inhomogeneity. There's not an example of field inhomogeneity here. Oh yeah, sample B. Okay. These are very common, but there are also some problems that are not so common, the susceptibility artifact or radio frequency interference. Well, in Biobank, we got almost all of these problems because we have so many subjects that it's impossible to prevent some of the problems. These are real cases in Biobank, including motion-induced problems, susceptibility artifact, or inhomogeneity in the field, or even that case, which is very weird, that we got the field of view completely cut. But these problems in our case are less than 2% of the whole set of acquisition. And we not only have problems with the acquisition, but sometimes the processing has also some problems, like there's a bad registration or the segmentation has problems, maybe due to the problems with motion. And as we have 15,000 subjects and we will have 100,000 subjects, it's important for us to be able to automatically detect those problems, and because it would be impossible to visually check all of the images. Sorry. And for that, we developed an automatic quality control tool, and that uses a set of quality control metrics that I developed. These are just some examples of the metrics: the level of asymmetry between hemispheres, the intensity in each subcortical structure for each modality. That's also one of the IDPs some of the IDPs that are available, or the amount of white matter that is out of the field of view on the diffusion images. And we are feeding all those features into a classifier, an automated classifier. And that classifier also uses a labeling of the original 10,000 subjects that I manually classified. And using that information, we are able to, the goal here would be to find subjects that are very likely problematic. I mean, not the subject, of course, but the image is problematic. So these are the results of the first 5,000 subjects. I'm showing this table instead of 10,000 because this table was published in a paper in Neuroimage. And in the first 5,000 subjects, we have 98 subjects that were classified as unusable because of processing problems or acquisition problems. And we are able to automatically detect 90 of those 98, which are the true positive in that table, but we missed 8 of those. The problem with these automatic classifiers is that you always need to find a balance between the false negative rate and the false positive rate. If we reduce the false negative rate like to 1 or 2 subjects that we miss, then the false positive rates would increase to almost the whole data set. So in this case, we managed to be able to just visually check 14% of the subjects, and we miss 8 of them. Right now, we are working on improving these numbers. There's a person working on using deep learning on the original images to be able to find these problems in both in the acquisition and in the processing. And this is a work in progress. And now I'm going to talk about some of the initial results of Biobank. One of the important results that we get is a set of, is the normative data. So in case that you have a 61-year-old male, you can see for different metrics what is the percentile in which that subject is. For example, for the gray volume, you can say that he's in the 21st percentile, or for structural connectivity, for hippocampal gray matter volume. And that information can be used by clinicians to help in diagnose or to be more specific with the treatment, for example. Another important result that we get is the possibility to find interesting correlations between IDPs and non-imaging variables. For example, here we saw a very clear non-linear correlation between the volume of the white matter lesions and the age. But this is just one of I talked about this before. This is just one of the examples of the correlations that we can find. And this is just using IDPs, just using the numbers, IDPs and non-IDPs. But we can also use the images, the processed images, to get more interesting results. Here I'm showing the correlation between fractional anisotropy and age. And this after Bonferroni correction, you can see that there's a general reduction in the FA related with age. But there are also some regions that show an increase in fractional anisotropy. That may be due to, it's very likely that the regions that have an increase in fractional anisotropy with age have more than one tract crossing in the same region. So there may be a loss of structure in one of the tracts in that region, and therefore the fractional anisotropy increases, even though there's a loss of structure. And you cannot see this kind of information just using the IDPs or the non-imaging variables. You need the images to have this kind of results. We have run 40 million univariate associations using the last batch of 15,000 subjects. And as you can see, even after Bonferroni correction, we get 15,000 significant correlations. The scale, the Y, is in logarithmic scale. So there are some correlations that have a p-value of 10 to minus 100, which may sound impressive, but actually we have to be very careful with this kind of numbers, because as I'm showing here, the significance, the number of correlations that we pass Bonferroni will increase exponentially with the number of subjects. And what is happening is that actually these correlations are do not explain a big amount of variance in the population. The power is not very high. So we have to treat not only us, every researcher using the data needs to treat all these big numbers with great care. Another problem with this kind of correlations is the problem of confounds, because some of these associations may be greatly affected by confounds. For example, here it looks like there's a very important correlation between the fat-free body mass and the white matter volume. But if we take a look at the sex of the participants, we see that there's a clear problem here. And if we adjust for those confounds, we actually see that there is no real correlation. So confounds, which is what I'm working on right now, it's a really important problem in these big data sets. And as I said there, one man's signal is another man's noise. So a variable that may be a confound for someone, and it's a clear confound for imaging, may be very interesting for some studies. For example, the blood pressure or the heart rate are affecting the functional connectivity IDPs, but also correlate with age and with some diseases, so it may be interesting. And also that the same happens with the head motion, that I have shown before that the head motion corrupts the images and corrupts also the IDPs that are generated out of the images, but is also highly correlated with age and with some diseases like Parkinson's disease. So even the removal of confounds, which is recommended, should be treated with care. Also, we are right now trying to model confounds related with the date of acquisition, because there may be drifts in the quality of the coils in the scanner, or the instructions given by the radiographers may get different with the acquisition date, because they may get sloppier or they may get more strict with time. So that may be affecting the results. And we are showing here how the noise to contrast ratio has been changing with the acquisition date. So we are right now trying to model that into the set of confounds that we are generating. This is basically what I'm working right now. I have divided all the confounds I could think about in different families, and I'm checking how each set of confounds explain the variability in the data. And as you can see, age explains a high variance of the population, but something as the table position of the scanner, which was something that we could not predict that was so important, apparently is also affecting the data highly. And we have now identified the problem, which is something that changed during the protocol acquisition. And so any conclusion that you may draw out of the data must have the table position as a confound. And finally, as I said before, we have to be very careful about all the confounds that you use and how you use them. And also we need to have in mind the Bergson paradox, because sometimes removing something that we think it's a confound may create a spurious correlation. So yeah, that's something that we are also studying right now. And well, I'm going to talk about the future of Biobank. This is going to be way shorter than I thought it would be. Sorry about that. So far, we have acquired the images of 23. I took this snapshot yesterday morning. So this is the number of subjects acquired yesterday morning. And these are the big issues related to analyzing this amount of data. The images of each subject amount of a maximum to 10 gigabytes. So that can be in total 1 petabyte of data. So that is an important piece of data that we need to have in mind. we are always having problems with the storage. Also, the processing of each subject takes 27 CPU hours and almost 1 GPU hour. That table explains how those hours are calculated, and the biggest part of the processing is done in the probabilistic cryptography, which takes 20 hours. But that is not even counting the time that resurfer takes to run, which would be 10 to 20 hours per subject. So these are important resources that need to be taken account for. Also, the 40 million univariate correlations that I saw before are just with 15,000 subjects. If you increase that to 100,000 subjects, that will need a huge amount of memory that no machine right now can support that. Well, no machine that we have access to can support that. So that will also be a challenge if we want to do that kind of analysis in the future. And also, we do our analysis of the images, but other researchers may want to do their own analysis. So biobanking is contemplating right now to offer cloud compute facilities for other groups or researchers to do their own analysis. And we encourage other groups to generate their own IDPs or variables, however you want to call them, and include them in the database, because the more information, the better. And something that we are also working recently is the correlations between genetics and the brain, and we are finding highly localized correlation between several regions of the brain and some SNPs. But we are also finding that some SNPs show important correlation distributed across the whole brain, which is something that we could not predict. And the goal would be to use all these correlations to better explain the structure and function of the brain, finding the genetic basis of the structure and the function of the brain, and be able to use that information to better inform in the classification of psychiatric diseases or development disorders. I don't know if you have seen this paper in Science, but this would be the end goal of what we are doing. This paper states something that many people think, that the labels used right now in medicine for some diseases may be a big umbrella that is covering many different things that are not as related as we think. So a person with schizophrenia may be closer to a person with major depression than another person with the same disorder. So actually using all these sources of information may allow us to find a better classification of the different disorders, and that may allow us to improve both the diagnosis and the treatment of all the diseases. And finally, well, these are some studies. Well, this slide is 1 year old, so right now there would be like, I don't know, 10 times more studies that are using the IDPs that we generate or the data that we are providing. And we would like to encourage all the groups to use as much as possible this resource, because it's very rich and it's very complete. That's it. Thank you. And so if you have any question, now it would be a good moment. Mm-hmm. But that curve was not the significance; was the number of significant correlations, which is not exactly the same. Uh, Not exactly. Well, yes, it does, but in a different way. We have restricted the the variables that we are using in that graph to only correlations that are higher than p to p equals 10 to minus 3. So what you are seeing there is just that kind of correlations. But the amount of variance is not affected. The amount of variance explained is by the confounds is not affected by the number of, of samples, not for the confounds. What happened? At some point, the radiographers, without informing us, activated an option in the scanner that did the auto positioning of the subject using laser detection. I don't know what it used, but they started using that. So, and the results of using that, which is provided by Siemens, are worse, way worse than not using that. So, after we detected the problem, we told them, and they stopped using that. But the consequence is that the table position is an important confound. If you don't have that in mind, you should remove all those subjects of those dates. And it's easier if you use the table position as a confound. Uh-huh. Yeah. That's what we are. Well, the software analysis, we are trying to have it fixed. The problem is that sometimes we are moving from one server to the other, but we are having that in account in the confounds that I saw before. But yeah, we are contemplating as I said before in the confounds, we are contemplating the acquisition date as a possible confound because the hardware may have problems that are drifting with time. The instructions given by the radiographers may change. It may also be possible that the healthiest subjects get scanned earlier than the seeker, which it's possible. I don't know if that's the case, but it's possible. So yeah, the date of the acquisition date, it may be important for any analysis that you do. So that's why we are recommending to use it as a confound. No, we have not found that. No, are you talking about the acquisition time of the day, or what are you talking about? Mhm. Yeah. No, we are not having that in mind, but that's interesting. Maybe we should start having the name of the radiographer as a confound here as well. The drawbacks, the main drawback is the the privacy of the subjects, because the original images are not defaced. They are not. They don't have we don't have the name of the subject, or we don't have the age of the subject is given to us as a range, so as we cannot identify easily the subject. But the raw images include the face, and that's a problem for privacy. We can analyze them in our lab, but putting them in a private cloud would be a problem. We are right now evaluating the legal aspects of all that, because we may want to go for that option, but we are still not sure. Yeah, but the defacing is a step that you have to take after you have converted the DICOM to Nifty, after you have done some small processing. So you need to do that. You cannot do that in a private cloud unless we can solve this legal question.
I'm an engineer. I know a lot of ideas about psychology, but I was really surprised about how you measure the age of a brain in this slide. For example, can you, because I understood that it was something related with the size of the functional. Can you show this?
Which one?
This was one where you measure the age of the.
This one?
No.
Earlier than this. Oh.
You should like, yes, this one. How do you determine the?
No. But so out of the data, we get statistics like every male subject of this age has this distribution, this probability distribution of the gray matter volume, for example. And then we can say, given a certain subject with a certain value of gray matter, we can tell where he is in the population. That's what I meant there. So I'm sorry if I was not clear enough.
Okay.
For that to emphasize also in this part of privacy, in this kind of data, important aspect in the next few years. So I don't know if you know something related with that to give a broad idea or summary of each consideration or implication or something we have, for example, to manage this kind of data or to upload to the cloud, or because it's mostly or even inside and outside from Europe is different.
Yeah. The laws in Europe of data protection are very clear. You cannot publicly share any data of patients if it's possible to identify the person. But that idea is very clear. What is not clear is how to interpret that. Because if you remove the face, you can say, okay, that is enough to avoid identify a person. But in the future, just having the shape of the brain may be possible for you, may make it possible for you to identify the person. Who knows? So we are doing as much as we can to have all the data as anonymized as we can, but it may not be enough in the future. So yeah, it's an open discussion. The probabilistic tractography is taking 20 hours, but those are 27 different tracks, so that part is parallelized. And each operation is actually parallelized. In each operation, we have a queuing system, the SGE, Sun Grid Engine, and that's the infrastructure that we have to parallelize all that. And we have a cluster with 500 CPUs, and that is controlled by this SGE. And we submit all our processing jobs to that cluster, and that's how we do all the process. No, but some operations like the eddy distortion correction are parallelized using GPUs, and that's why they only take half an hour, because otherwise they would take one day. But the registration is not parallelized using GPUs, for example. But as we have, when we process this, we have 5,000 subjects, so it's okay if we run one per CPU, because we will take all the CPUs that we have. Does that answer your question?
Yeah.
Yeah. Thank you.
Ok, pues ahora podemos empezar lo divertido. He ofrecido a Carlos que te haga un pequeño tutorial sobre ¿sí? Claro, de la clase completamente improvisado. Y todos aquellos que realmente